Now let's talk about um, the one forms, or so to say the cotangent vectors. Since we said that this tangent space is a vector space, let's say we're writing vector space as v dot s, an acronym. This means vector space. So there should be a dual space, a dual vector space to this, and we are calling it the cotangent space, and we denote it with P star at m, at point P on M. And the elements of this cotangent space are denoted by this omega. These omega elements are such that it acts on the vectors and brings out a real number, or it maps to R. Okay, the simplest example of a one form or a cotangent vector on a manifold is the differential df. Example, this is a one form. We'll talk more about forms later. For now we're calling it a one form because you can think of it like this: by saying one form there is just one t, but it will be more clear when we'll talk about differential forms. Alright, now the action of a vector, if you can recall the discussion that we were having 5 minutes ago, was something like this. If you have a vector v, we used to denote it by x, but now let's say it's v, it's acting on f. This is just v mu df dx mu, right? And this is what? This is indeed something that belongs to R, right? So the action of df which belongs to the dual space on the vector v on the tangent space is defined by using this symbol. This is a angle bracket, you can call it an angle bracket, and we want to have a real number out of this, right? But we already saw that if a vector acts on a function, it also produces a real number, so we can call it v of f like this, and ultimately we will get what we want, right? So we can see that this product or this operation is R, that means it belongs to R, and this is linear in both f and v. Now note that our df is expressed in terms of the local coordinates, right? That is, what I'm saying is that this differential is actually coming in terms of the local coordinates. So you can take this differential and expand it in terms of the local coordinates like this. Since we are calling this cotangent vectors or one forms, you can treat these quantities as the components and this quantities as the basis on the cotangent space. Okay, so this dx mu are basis elements of t star p. Also, since this cotangent space is dual to the vector space itself or the tangent space, we have the following relation between these two basis vectors. Okay, let's call it new. This is just mu del x new, and this is just delta mu new. So we have now the basis for the dual vectors. So what we can do is that for any element omega, we can write any element on the dual vector space as this. Okay, and these are one forms as well. As you can see, we're calling it one forms, and again it will be clear later why we're calling them one forms. For now, you can just think of it as, if you have this d of a differential attached to something, we are calling it as a form. And these are your components, obviously. Components, these are your bases. And now, since we have a vector space and a dual vector space, the next natural thing we can do is that we can define their inner product. So the inner product between the tangent space and the cotangent space, let's write it like this. The cotangent space with the tangent space to R is defined as follows: omega v, note that omega belongs to T star m at P, and v belongs to Tp of m. Then we can expand omega as omega mu dx mu, and we can expand this as del v, let's say rho, del x rho. Since these are components, we can bring them out. They don't play any essential role. Omega mu v rho, and we have del x mu del x rho, omega mu v rho, delta, sorry, it should be mu, delta mu rho, and finally we have omega mu v mu. This is the inner product. Again, just like vectors, you can see that if you choose two coordinate systems by x and y, just like we did with vectors, you can see that this omega itself is invariant as this. Let's say omega mu tilde dy mu. So you can see that the basis can change, the components will change, but the quantity omega, the cotangent vector itself, is invariant. And you can even show, so take this as an exercise to show that your omega tilde mu is equals to omega tilde, okay, sorry, it shouldn't be mu, let's write it as nu, that's convenient. Nu omega mu del x mu del y mu. Again, a hint is something like this. Since you are doing it for a single point, you can have two charts that such that the point itself belongs to the overlapping region. Then it's just a matter of mapping them to Rn and using the identity map as the coordinate map. With this, you can show this very easily and rigorously. Now let's talk about something called tensors. Please note that this is not a tensor analysis course, so we won't go in depth. We will just define what tensors are. So you can think of tensors as generalizations of these vectors and forms. So a tensor, it is a multilinear object. Multilinear object of type QR, let's say, which maps Q elements of T star PM, that is the cotangent space. So you are writing the amount of form that the tensor thing has inside it, and are elements of TPM. That means it's taking Q forms or Q1 forms and R vectors and maps them to real numbers, to a real number. In general, the tensor can be written as, let's say, T. You can write it as T mu1, mu2, mu q, and then nu1, nu2, nu of r. This is your component, and then you write down the basis. Let's say mu1, mu q, then you have dx mu1, nu1, dx nu of r. Okay, and the reason we were calling it multilinear, because on vectors and one forms you saw that there is only one matrix, or so to say, there is only one transformation matrix. But if you compare that thing with this guy over here, the component, you see there are tons of indices, right? So all of these indices will get transformed by some sort of a matrix. So that's one of the reasons we call it a multilinear. So if you have some t tilde, it will be related by some lambda 1, lambda 2, lambda 3, some lambda and then t. I'm not writing this in the index notation, but I think you can understand what I'm actually trying to say. So this is a multilinear object or a multilinear transformation. Now that we discussed these tensors, let's talk about something called fields on a manifold. So what happens if we assign a vector smoothly to each point of n that I was talking about earlier? That if you have a manifold like this, you have these curves that are non-intersecting, you can have tangent vectors at each point, you assign them, and you have a vector field. If you wanted a scalar field, you would assign some number to each point, right? Something like this. Similarly, like a vector field, a scalar field, you can also define a tensor field by saying that we define these tensor fields of type QR, let's say, by a smooth assignment of an element which is a tensor at each point in the manifold. So this is how you can construct tensor fields as well. Okay, example of scalar fields can be your temperatures. So this is a scalar field. I think you are very familiar with vector fields. It can be gravity, it can be electricity or electric field, not electricity, sorry, electric field. It can be magnetic fields and so on. And you can even have fields that are very exotic, and those type of fields are called matrix valued fields as well. Instead of assigning scalar vectors or tensors, think of assigning a matrix at each and every point on that manifold. That will give you some matrix valued fields as well. Okay, and you'll see more of these things if you study quantum field theory or non-abelian gauge theory and string theory and so on. But now we want to go back to our main discussion. That is, we were talking about the calculus on manifolds, and we would like to move forward by talking about induced maps.